Hey, fellow mathers! Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam-packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over $6,000 worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, fellow mathematicians! You're listening to the podcast where math is figureoutable. I'm Pam.
And I'm Kim.
And you found a place where math is not about memorizing and mimicking, waiting to be told or shown what to do. But y'all, it's about making sense of problems, noticing patterns, and reasoning using mathematical relationships. We can mentor mathematicians as we co-create meaning together. Not only are algorithms not particularly helpful in teaching mathematics, but rotely repeating steps actually keep students from being the mathematicians they can be.
In this episode, we plan to continue the conversation around decimals and begin to answer some questions around decimal multiplication. So we got an email from a listener, Willow, and she said, I was hoping that you ladies could do a podcast on multiplying decimal numbers less than 1 and a way to model or help students figure out what's happening when you multiply 0.3 times 0.7. Halves are easier to explain, but the concept does not always transfer because 0.3 is not 1/3.
So it's always funny to me when you say 0.3 instead of just 0.3, but it's okay. Sorry. I think it's because you're reading it off of the email.
Yeah.
So we don't usually say 0.3. We usually just say 0.3 or 3/10.
Do you not?
I don't.
I sometimes do. Yes.
Huh.
It's so funny that you say that. I do say 0.3.
I don't think I've ever in my life said 0.3 unless I was writing on the board. Okay, maybe not important. I don't know. All right. However, it can be important that we say 3/10 sometimes, not just 0.3. But I will often have middle school teachers say to me, don't say 0.3. You have to say 3/10. To which I will say, okay, common language is 0.3 and kids need to hear both. So I think they need to hear both. Not only one, but they need to hear both.
Have you ever talked to a 4th grade teacher? They're cringing right now. They're absolutely losing their minds about me saying point.
Because they want you to say 3/10, not 0.3.
Oh, never say point.
Well, I mean, same thing with a 6th grade teacher. So they're in the same boat, and we're going to disagree with both of them. We need to say both. Kids need to hear both. Now, in today's podcast, we are going to say 0.3 and not 3/10 because for communication's sake on the podcast, we want you to sort of hear what students are seeing because we're in this sort of verbal kind of a place. So we might use both a little bit, but for the most part, we're going to say point in an attempt to make sure that we're all talking about the same representation. And so that's why today you're going to hear us. Though I don't know that you're ever going to hear me say 0.3, just 0.3, but it's all so good. Funny. Okay.
You'll have to think about that. Okay.
All right. So today's episode, we are going to answer Willow's question kind of in a couple of ways, or maybe I should say 2 parts. So we want to suggest that it is really important that students actually understand and feel the relationships involved in a question like 0.3 times 0.7 first, before we get very sophisticated and efficient at solving that problem. Not because it needs to be concrete and then representational and abstract. It's not about that. It's much more about we actually have to feel the relationships that are happening, and then we can get more sophisticated, which doesn't necessarily mean just symbols. It means then actually using more sophisticated relationships. What do we mean by that? Well, let's get at what first it means to multiply by 1/10 or 0.1, what does it mean to say something times 0.1? To do that, we're going to do my favorite instructional routine ever, a problem string. Kim, I'm asking the questions today. You get to answer. Here we go.
Can't wait.
First problem of the string. What is 8 times 0.1? 8 times 0.1.
Okay. So that is, I know 0.1 is like a dime. So it's 8 dimes. So 80 cents.
So you're saying it's 80 cents. Okay. 0.8.
Mm-hmm.
Cool.
Mm-hmm.
I might represent that on the board. I might write the problem 8 times 0.1 equals, and then she just said 80 cents. So I might write 0.80. And now on the board, I'm going to write 0.80. And the 0 on the board that precedes the decimal is all about readability. I want that decimal to pop on the board. And so I'm going to write that leading 0, 0. And then I might also write 0.8. And I'm also going to represent that as the dimensions of an array. And you didn't say this, Kim, but I might ask students, could anybody think about that as the area of a rectangle that is 8 by 0.1? What would that look like? And I might ask students, what would a rectangle look like? And then I might represent that as a long 8 by a little tiny 0.1, right? I mean, like 8. And I'm probably not going to even do that on the board because it would like take up too much space to be exactly proportional. But I'm going to have a long 8 by a little 0.1. So we're going to have a really tall, skinny rectangle. I'm going to put those dimensions up there. And the area inside, I'm going to write 0.8 as the area of an 8 by 0.1. Cool. Next problem. What is 8 times 0.3?
Okay, so that's
3 tenths. Go ahead.
Yeah, that's going to be 3 times as much as what you just asked for. So it's going to be 2. So 8 30 cents is $2.40.
So I kind of heard a couple different thinking. You could, I heard the 3 times as much. So you could think about what 3 times 0.8 or 3 times 80 cents is. And you're saying that's $2.40. So I just wrote down, I already had written down 8 times 0.3 or 0.3 equals, and then I just wrote down 2.40 because you said $2.40. So I'm going to write it like money, 2.40. I could think about it as 2.4. I'm going to also then ask that 3 times as much, 3 times. I might scale that rectangle. Is anybody thinking about the rectangle? If an 8 by 0.1 is this tall, skinny rectangle, then what would an 8 by 0.3 look like? And sure enough, it'd be that dimension would be 3 times the length of the 8 by 0.1. Now that 0.3 is 3 of those 0.1s, right? So I might put that up on the board. I might be like, okay, 8 by 0.3, and you're telling me the area of all of that is 2.4 or $2.40. I also might have started this problem string by saying, we're kind of dealing with 8s here. And now we know we're dealing with 8s because we have 2 problems with 8s. And so I might also have a ratio table that says I'm dealing with 8s. So I've got 1, 8. So I've just in my ratio table, I've got a 1 and I've got an 8. And then I might say that first problem asked for a tenth of 8. And so then in that next slot, so I'm doing a horizontal ratio table. I've got 1 and then 8 on the bottom. And then next to that, I've got 0.1 or 1/10. And I might say, so how do you get from 1 to 1/10? You guys are telling me that's like divided by 10. So can I also think about that 8 divided by 10? And 8 divided by 10, I can think of in a couple different ways. I can think of that as the fraction 8 tenths. But I can also think about that as 0.8, sort of divided by 10, and it's kind of a place value shift. But then that second problem, 8 times 0.3, you said was 3 times. So I could, in that ratio table, I could scale that 0.1 times 3. So I've literally just drawn an arrow, and I've said from that 0.1 times 3, then I'm going to have that 0.8 times 3, and that's the 2.4. So I kind of have a ratio table now with 3 entries, 1 to 8, 0.1 to 0.8, and 0.3 to 2.4. And what are you laughing about?
I'm laughing because it's exactly what I wrote.
Yeah, nice.
You just described like what's on
your paper. Okay, very cool. Next problem. What is 8 times 0.05, 0.05? 8 times 500ths. Or as Kim would say it, 0.05.
0.05. Okay, so I already have 8 times 0.1. And so it's going to be half as much. And so I divide it by 2 or times it by half. And so I in my head, I thought, oh, that's like 8 nickels as well. So I was confirming with money because I considered dimes at the very beginning. And so half as much would be a nickel.
Half of 80 cents.
Half
I would go
of
back
80
to that
cents
80
would be
cents.
40
And I was
cents.
like, yeah. So if that nickel is half of a dime, then half of 80 cents is 40 cents.
Yep.
But you also then said you're checking that with knowing that you've got 8 nickels, and 8 nickels is also 40 cents. Cool. And then I might on the board as a teacher take that 8 by 1/10 of that 8 by 0.1 rectangle, and I might cut it in half. So now I have an 8 by 0.5. So I had to be careful knowing I was going there that what I drew on the board at that 8 by 0.1, it was pretty tall and pretty skinny, but it wasn't so skinny that I couldn't then cut it in half and get an 8 by 0.5. Oh, then therefore half of what we had as 0.8 now is 0.4. Cool. Next problem. What is 8 times 0.15? Or as Kim would say, 8 times 0.15.
You're going to catch me every time now.
I'm probably bugging you.
Okay, so I know I have the answer, but I'm trying to decide which way I want to share with you because I've got a couple of different ways to get there.
Okay, so share slowly. Share the first one.
Okay. So because it happens to be the previous problem that you asked, the nickel, I noticed that it's going to be 3 times as much. So 15 cents is 3 times as much as 5 cents. So 3 times as much as the 40 cents will be $1.20. So it's right next to it on my ratio table. You had just asked 8 nickels and now you're asking 8 15 cents. And so it's going to be 3 times as much.
And I literally on my ratio table drew the arrow and said times 3 of the 5 nickels is 15 cents. So times 3 of the 40 cents is $1.20. Cool.
But I looked back a little bit further.
Yeah.
Oh, you want to write that?
No, go ahead. No.
So I looked back a little bit further, and I noticed that you had also.
I'm sorry.
Okay.
I'm sorry. I can't stand it because when you say that strategy, I want to go find the 0.05, the 8 by 0.05 rectangle, and I want to redraw it on the board, and then I want to scale it times 3. And say, okay, so once we had this, and you're saying I can see, and I just want to sort of show that happening times 3. Okay, now do your other one.
When I looked back to previous problems, I remembered that you had asked me about 8 times 0.3. And the product's going to be half as much as 8 by 0.3, which was 240. And so now it's
15
1.2.
cents is half. Sorry, I'm interrupting.
No, it's okay. 15 cents is half of 30 cents.
Cool. And so the 30 cents corresponded to $2.40. So you're saying you could do half of $2.40 to get the $1.20?
Yep.
That is totally cool. Should I admit that when I prepared this today, I didn't see that relationship? I had not thought about that one, Kim. Good job. Nice. That surprised me a little bit. I thought you were going to do another one. You got one more?
Yeah, there is one more. And so it's adding the dime and the nickel together. At least one more, yeah. Adding the dime and the nickel together to get to 15 cents. So adding the 80 cents and 40 cents to get $1.20.
Damn.
And I'm glad you said at least one more because
we never want to limit our students
because it's one more than I had seen originally. Yeah. I'm sure there's more.
Yeah, there you go. We never want to limit our students by what we can think of. And so when you added the tenth and the dime and the nickel together to get the 15 cents, I would have taken those arrays, those corresponding area models, rectangles, and added those together. And then clearly we could sort of show that partial product. Nice. Last problem of the string. What is 8 times 0.35? 8 times 0.35.
5. So my first thought is the 30 cents, the 8 times 0.3 was 240. And then right next to it was the 8 times 0.05.
How convenient.
Right. And so that's $2.40 and 40 cents, which is $2.80.
And you've literally taken chunks chunks that you can think about, chunks you can reason about to find the answer to a problem like 8 times 0.35, a decimal multiplication problem. Nice. Now you might be thinking, okay, but Pam, only one of those numbers was a decimal. Sure, but we're going to start somewhere. We're going to start somewhere and we're going to do some partial products, and we're going to do some smart partial products where we're asking students to actually grapple with these relationships and comparing to money and using area to bring those relationships together to help students really think and reason about what's happening. To be clear, we're not going to stop here. We're not going to say, okay, so every problem you get, we want you to walk back to 8 times with 10th, and then work your way up with all these chunks. No, we're going to get more sophisticated. In fact, we're going to get really sophisticated and efficient fairly quickly, especially if students have already built whole number strategies, because the strategies, the multiplication strategies for whole numbers are going to hugely impact the way that we multiply decimals. But we're going to back up at this point. Even if our students are really good at multiplying whole numbers, we want to get this sense and this feel for what's happening when you're multiplying decimals. So the problem string that we just did is a great place to start. I don't know, Kim, if you want to say anything before we do the next string.
Oh, no.
No? Okay, I'm just checking. Just making sure there wasn't anything bubbling out of you before we head on to the next one. So then how do we get a little bit more efficient? Well, then we want to, get a little bit crankier, where we've got a little crankier numbers. It's not just 8. It's not just, a little bit of decimals. But we might do a problem string like, so Kim, here we go. What is 2.3 or $2.30, 2.3 or 2 and 3 tenths times 2?
Oh, okay. I was prepared for
You're
more
like
complicated. Okay,
not yet,
so
not yet.
$2.30 doubled. I like doubled is $4.60.
Cool. And so I'm probably going to represent this in a ratio table. And so I might say 2.3 is 1 to 2. The first starting with the ratio of 1 to 2.3, and then we got 2 of them, and you said that was 4.6. So now I have a ratio table of 1 to 2.3 and 2 to 4.6. I might do that. I also, in a separate, I don't think I would do these two together for this problem string. I could, and maybe should be. So this depends. Which model am I going to use to model this string? I have this conversation right now in my head. It depends. If I have students who are well-versed in ratio tables, I might now just be using ratio tables.
Yeah.
If I have students who are really just beginning to think about decimal relationships, I actually would probably model this on a rectangle. I would probably use an area model here first. So I would have a 2.3 on one dimension and a 2 on the other. And this is going to look very square-ish because 2.3 and 2 are very close together. So almost square, not a square, not a perfect square, but almost square, a little bit taller than it is wide. So 2.3 by 2. And then you told me the area that was 4.6. Next problem. What is 2.3 times 0.2? Or the area of a rectangle that is 2.3 by 0.2 or 2 tenths.
Yeah, it's funny that you say that because I wasn't sure where you're going, but I know that 0.2 is a tenth of 2. So I just scaled down my 4.6 by 10, by a tenth. I multiplied it by a tenth, and it's 0.46. And when you were talking about your area model just right now, I pictured the area model like scaling down, like it got skinny all of a sudden.
Nice. And so I might model that as a 2.3 by this really skinny 0.2. 0.2, and the area of that you just said was 0.6. Look at that. I just said it like you would. 0.46. Cool. Next problem. What is 2.3 times 4?
Okay, it's going to be double when it was 2.3 times 2. So 2.3 times 2 is 4.6. Doubled again is 9.2.
And you double that 4.6 really fast. We might have some conversations about kids doubling the 4.6. We're going to give them some experience thinking about doubling. But for today's podcast, we're just going to run with it. So a 2.3 by 4 would give you an area of 9.2, sort of double what you had from the 2. Nice. Last question. What is the area of a rectangle that is 2.3 by 4.2?
Okay. You gave me the previous pieces of 2.3 times 4 and 2.3 times 0.2. So I'm going to add those together, which is 9.2 and 0.46. And so that is 9.66.
And I would probably draw the rectangle that would be 2.3. And I would maybe even add on to the one that we had that was 2.3 times 4. And I would say, how much bigger is this? Oh, it's this little rectangle we had up here. It's this 2.3 by 0.2. I draw like a dotted line and I would like move it down there and I would say, oh, there it is. It needs to be right here. And I would sort of tack on that little rectangle on the end and go, So I could think about 2.3, a rectangle that is, think about the area of a rectangle that is 2.3 by 4.2 as a rectangle that is 2.3 by 4 with that little bit of a 2.3 by 0.2 tacked on over there. And notice how that's smart partial products. We're not breaking it up into all 4 chunks, though we could, and I would be okay with you doing some problems like that. But fairly quickly, y'all, I want you to move to helping kids think about smart partial products. What are some of the things that they know that they can use to help them, that they don't have to just cut it all into all 4 sections? Also notice that I made a deal about how we are making sure the rectangles are in proportion. Here's what I absolutely am not suggesting is that for a problem like 2.3 times 4.2, that I'm drawing a square and I'm cutting that square into 4 equal pieces. And then I'm writing down a 2 on the dimension of 1 and then a 0.3 and then across the top a 4 and a 0.2. And I'm pretending that I'm just like that has anything to do with area. No. Like let's let the magnitudes of those rectangles represent what they should. Let's have them be proportional. Y'all, if you're doing problems like this, kids are learning proportional reasoning. And one of the ways we're going to do that is to actually draw the area models proportional because then they actually can. There you go. All right. So Kim, we got to finish this podcast by answering Willow's question. So Willow's question was, what is 0.3 times 0.7? 0.3 times 0.7. Well, Willow, I would expect that if students had done the work that we just did with Kim today on the podcast, we just did with everybody on the podcast, that students might look at that and say, 0.3 times 0.7, what do I know? Well, I bet I could find a tenth of 7. Of 0.7. I could find 0.1 times 0.7. So if I've got 70 cents, can I find a tenth of that, 0.1 of that 70 cents? And let's see, a tenth of 70 cents, is that 7 cents? So that's 0.07. So if 0.1 times 0.7 is 7 cents, then I think a kid could think about 3 times that to get from 0.1 to 0.3. They could multiply by 3. And what's 3 times 7 cents? 0.21. Now you might say, Pam, I don't know if kids will think about times 3. They might like, well, I got 0.1 times 0.7, but now I need they might go 0.2, so they might double it and then add back. But still, either way, they've got maybe but they've got 7 cents, and they might get 14 cents, and then add the next 7 cents to get 21 cents or 0.21. But I think that's how a beginning multiplier who's actually understanding what's happening to solve 0.3 times 0.7. Find 0.1 first, and then scale it up to get the 0.3 times 0.7. What do you think, Willow? We are interested to know. So let us know. Let us know, everybody, what you kind of think about how we are multiplying decimals. Now, again, this is how to start, so kids are actually understanding what's happening. You might be thinking, Pam, we don't have time for that. Like, all I have time for is, you guys, just use the algorithm and then butt cheek at the end. Because you might be used to only spending a very little time on multiplying decimals. Because if kids are already multiplying with the algorithm, then you just kind of use the same algorithm, but then move the decimal at the end. We are suggesting if you can get kids actually thinking and reasoning, using anything, if you can get them actually thinking and reasoning, you will have to redo and undo less. And that is where we're going to save you time. We're going to actually understand it here. Then we're going to get more sophisticated at it. And we are going to take some time to do that. But then we can undo and redo less. How? How are we going to get some more sophisticated? Well, stay tuned. In the next episode, we are going to get at that. We're going to get at how we can get more sophisticated and efficient while maintaining kids actually understand what's happening. So y'all, thanks for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at maththisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's maththisfigureoutable.com/challenge. Join us to make math more and more figure outable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.